Good morning, everybody. Hello. Hello. My name is Björn. Today I'll be giving you a lecture on how to stay organized in machine learning projects. I am an instructor here in the CV4 Ecology, as you might know, and I just finished my PhD in machine learning, also at the intersection to climate modeling at MIT, and now I'm here for the summer. Okay, how to stay organized in machine learning projects. Maybe let me get started with one story out of my personal life, out of a friend's personal life. 2 years ago, they were in an internship similar to yours, and there was 5 people working on a project. It was super fun. They coded a lot and created folders, structures, Python files. The machine learning project ran somewhat, but then it was about time to write the paper, and we started looking at our code, and even though it was so much fun to create the code kind of looked like this, and we were all like, how are we gonna create some reproducibility here? We want to publish that, share that with other collaborators, and all they're going to see is this mess of colors that we have created. So this might be a story familiar to some of you. The good news is, hands up who has already their code on GitHub or has created a project on GitHub. That's amazing. That's the first step to staying organized in your machine learning projects. You've already done that. You've created the conda environment. Most of you set up some form of developing environment, gained some familiarity with the remote workflow. And today we're taking the next step here, which is how to set up our workspace. And basically the structure of this 1-hour lecture will be that there's one repository on GitHub, on our CV4 Ecology school GitHub, that was created by Benjamin Kellenberger, an instructor from last year, called CT Classifier, which is somewhat of a bare bone code structure that we recommend you to start off with when you develop a classification or a detection or a segmentation algorithm. So this code base and the lecture today contains a workspace setup, meaning how do we, which folders do we create, which files do we create in those folders. Then I will go into how do we structure our hyperparameter experiments, meaning that if you have one model, once you have one model running, you will think about what are all the experiments, the things you can now try to improve the accuracy of that model. And that's probably one of the most challenging aspects to stay organized, because it's so exciting to try a new model. Then the deep learning code base, what are the bare bone elements that should be in a deep learning code, the bare bone Python files. And then lastly, when you do start to train your first model, probably at the end of this week on Friday, how to progress and how to monitor this training progress and know that you're doing something useful. So during this lecture, I'm somewhat assuming that you are familiar with Python and various structures of Python. No worries if some of these terms are new to you or not that familiar. Just ask your TA or instructor later on about them to re-clarify. I'm going to assume that you know what data structures are, such as a list, a class, a function, a dictionary, what the difference between object-oriented and function-oriented programming is, what namespaces are, and what scope is. I'm going to assume you have some basic familiarity with how to comment the code using style guides, meaning that the variable names that you're defining have some form of structure to them. And some familiarity with Python libraries such as NumPy, Pandas, and Matplotlib. Another resource beyond your instructor or TA is also the book Python for Data Analysis by O'Reilly that we recommend. So the workspace setup. One of the main lessons probably is that 2-3 years ago when we started that internship project, we really should have taken a break in the very beginning and just set up a nice code repository and then add to that repository. So one of the main lessons is do it properly and do it now in the beginning of your project. And when doing so, one of the objectives is to write modular. To create something modular. So with these building blocks, you can see here, modularity means we're writing separated code files or separated folders, for example, for our data, for a code in our experiment, so that when we have new data coming in, we don't need to rewrite any code. Or when we change our code, we don't need to rewrite any folder names or file names in our data. So that's the idea of modularity. We want our workspace to be set up in a way that it is easy to share with collaborators, and we don't need to be embarrassed when we share it with them. Also, in 1 or 2 months or in a year, when you might look at your code again, be kind to your future self and not make them rage about who in the past created this, this mess of colors. Reproducibility, I think machine learning, computer vision in general has always struggled with reproducibility. The idea is that if you do publish a paper, somebody should be able to reproduce every plot that you create in your paper using the GitHub and the instructions that you put onto that GitHub. And lastly, papers that are shared on GitHub get more citations, and also just makes it easier for anybody in the world to use, maybe with a startup or with people that might not have access to the higher education system. They can go onto GitHub and at least see the code. To do so, though, you have to define proper policies, a proper license that people are allowed to use your GitHub code. Okay, so that brings us to the structure of this GitHub repository that I was talking about. The GitHub repository has about 10 folder files at the highest hierarchy, and it is a bare-bone classifier of camera trap imagery. So it's called CT classifier, camera trap classifier. We will go over these items one by one. So the first item is the .git. That's a hidden Git folder that contains all the commit history and everything that Git needs to, it might happen that you accidentally delete some files. If you have committed them in the past to Git, they would be stored in that .git, and using that and the proper Git commands, you can restore those files. So don't delete that Git folder, that .git folder. But it is also backed up in Git, so you can't accidentally delete it. There's a git ignore that contains all the files and folders that you do not want to be uploaded to Git. So for example, if you have your data in this folder, add the data to that .ignore or all kind of auxiliary files. Your main code, all the magic of the Python and what's happening, that goes into the main repository, into the main source code, which is named in the same way as the repository on GitHub. Name. This name will be sort of like the advertisement of your project. So for example, camera trap classifier, Chris might want to call his guano segmentation, or Michael maybe predator classification or predator detection. These give you an easy understanding of what your project will be about. So from the source code, which we will dive into more in section 3 of the lecture, we go to data. The data folder contains all the data, and I like to store my data within my project to keep it organized. But I think for this school, we do recommend you to store it on Mount SSD cluster/user, and then link to that data in your Python files, respectively. The data, in this case, has 3 folders: raw, interim, and processed. And this slide is basically, I could hold a whole lecture on data management, but maybe one of the essentials is that a raw folder is created that contains all the external immutable data dump. So if you have a camera trap, and you just pull all the data from that camera trap, or you have some microphones, you pull all the data from those microphones. In the original format, that's where you put them into a raw folder. And then you start processing the data, maybe changing file names, folder names, maybe extracting things like a spectrogram from audio files. Those go into the interim folder. And then lastly, the process folder that contains data in a way that it is formatted exactly in the way that your machine learning project, that your machine learning model wants to see the data. So, so in that processed folder, I like to have one folder that is the subset of the data. So, for example, that's the 2 GB chunk that you decided to use for this computer vision for ecology school, or the 10 GB, and then one JSON file or one CSV that contains the file path, the file names to every one of your images or every one of your data samples, including the metadata and all the other values that you want to know about this sample, so that you can do proper train-val test splits like Sarah explained yesterday. So those will all be in that JSON file. Sometimes some specific models, they require a format of this file. So for example, we can recommend the COCO format. So you have that data folder. With that data folder in hand, you can go to the next folders, which is documentation. I like to keep a subfolder in that called figures that contains all the matplotlib figures and everything that I produce. I also like to keep my paper drafts in that folder so that it's automatically synced to GitHub, and all the kind of explanatory material that others might need when they want to understand where your data come from, which exact microphone did you use, which exact camera setup did you use, what were the calibrations on those cameras, all those kind of stuff that can go into the documentation folder. And then the policies to share your GitHub, that's important, is the license file. If you forget to add a license file to your data set or to your code and you want to share it with people, by law, it automatically means that you have associated the most strict license possible to your GitHub. So you do need to, so if you want somebody else to use your code, you should add a license file. One of the most popular ones is the MIT license, which means you can do whatever you want with the code. You can use it commercially, you could use it in academia, you could use it in anything else. But if you do use it, you should credit me somehow for using it, maybe by a citation. And then there's all the other licenses, which are various combinations of can you use it commercially, can you use it academically, can you if you do decide to use it, can you change the license, or do you need to keep the same license? Those kind of things. Then notebooks, that's a folder that I allow myself to sometimes get a little messy in. Notebooks can contain, the notebooks, one important one often is how to create the interim data from the raw data, or how to create the process data from the interim data, so that you can reproduce that and don't need to, every time you have new data coming in, recreate all those commands that you have done in the past. I like to keep a Jupyter notebook of data exploration. That's the visualization, the assignment 0 that you've already done. That goes into this folder. And then often, after the model has been run, maybe you might want to explore the visual quality of the bounding boxes, or I think you have like a Ben's doing some unsupervised learning. You might want to plot the features and the feature space that can go into like this exploration of the results notebook. And lastly, there's a README file in every GitHub repository that I want to talk to you quickly about. It contains the title of the project and an overview what the project is about, but most importantly, it contains the installation instructions. And if you do use Conda, those installation instructions will be very easy. They'll be like git clone and then Conda install, and then you basically have everything set up. The user instruction, so this will in the ideal case, that's 1 or 2 lines that contain something like Python train.py paper configuration. And using this command, it should ideally create the plots that you have in your paper. And then lastly, a citation information on how to credit you for this code. The requirements, the text, or the environment.yaml contains all the environment on running your code, like the conda configuration. And lastly, the runs folder contains all the hyperparameter configurations and the training logs and all the experiments that you've conducted. That folder is so easy to get messy with, so that deserves a whole new section on how to organize your hyperparameter experiments.
Sorry, so for the similar to the requirements.txt, is it useful to include your YAML file, or is that something that might be very specific to your machine and wouldn't work?
Like the environment.yaml you're asking, or the config.yaml?
The environment one, I guess.
Yeah, I think usually we do either a requirements.txt or a environment.yaml.
Oh, okay, yeah. So it's something you can use. It's something you can put on there that could be useful, the YAML file.
Correct. Yeah. If you don't have a requirements.txt, you should put an environment.yaml.
Okay.
Yeah, the requirements.txt is used by pip, and then environment.yaml used by conda. So depending on whether you want people to set up your project with pip or with conda, you do either one.
Okay.
Any other questions on this before I go on to the next section?
Do you have any recommendations on how to organize the docs folder? Because that's where you keep all of your paper-related materials.
Yeah. So any recommendations on how to organize the docs folder? Let's see. I like to have one folder in there called figures, right? Store all the plots. One folder with paper, where I draft the actual paper, and then one folder that's kind of messy that contains all the other things. Yeah. Okay, how to organize your hyperparameter experiments. The main takeaway, please don't do this, have like a long list of file names that contain something like I wanted to try and learning rate, maybe with some weight decay, those are hyperparameters. I randomly initialized my weights, that's a new experiment. And then also there's some other experiments, and here I ran out of file names, so I just added some. And then the model checkpoint. This is basically how our code looked at the end of the internship. So how to not do this is you can create this folder structure. Some of our instructors recommend. We like to have a first hierarchy of the model name. So maybe that might be a ResNet or a YOLO or whatever other model you experiment with. Then an experiment name. So this could be the train by test split that you're working on, yep. And then also a default. I often have a default experiment name, which is the experiment that just gets overwritten all the time, where I can experiment with, and that can get a little messy. And then each experiment will contain a config.yaml. That's very important. That contains all the hyperparameters that were used for that experiment. It contains a log folder that says how the training progressed over time. This is usually automatically created by like a logging toolbox that the last part of this lecture will go over. There's a checkpoint folder. This checkpoint folder contains all the weights, the actual physical float, not physical, but the actual float values of the model that you're using, so that you can share that model, give it to somebody else, and they can load it in the code. Usually I have that folder added to the git ignore, because those model files can get pretty heavy. And then the predictions, that can be ideally a JSON file that's in the same format as the one in the data, so that you could take only those two files. And if another collaborator has a completely different model and code setup, maybe they are not even using deep learning, but some form of traditional computer vision, but you do want to compare the results with that method, you ask them to create the JSON format in the same format, and that goes into predictions. And then you can use that notebook that IPY by to visualize both results of both models.
Keep that under the runs folder? Is that where like each model name would be a subfolder in runs, or is that its own top level folder?
Yes, yeah. Runs, and then runs has multiple model names. Each model name has multiple experiment name. Each experiment name has one config.
Thanks.
How to organize those experiments? Once I start coding up and running my first model, I usually get incredibly excited and just looking 10 minutes at the training curve, I already have all these ideas, like what if I change my learning rate? What if I try this new split? What if I change the weight decay? But most of the time I can only run one experiment at a time. So the important lesson I think here for me personally is to hold myself back. Don't run any future experiments until I have a very sound baseline that I do understand, and that I know where I understand the train and where I understand the test set about. But to keep that excitement going, I like to put all those experiments that I can think about while training into a prioritized to-do list of future experiments, so future and past experiments that contain things like the experiment ID, the experiment name, the hyperparameters that that the model had and that I want to try, and then the results of that. And Justin and Suzanne, they have the same approach, and they're very happy with it. Usually they keep it in a Google Sheet, so we can recommend that. So the deep learning code setup, we're about halfway of the lecture, so I would like to go into a think, pair, share activity. Given what you just seen, what did you like about the structure and organization in your past projects? Please go with the person next to you, and then you have about 3 minutes to talk with them, brainstorm.
Well, think first, or
Yeah, I guess.
You mean in your own house?
I haven't liked anything about
I have to record training architecture is separate.
It says me it's not. Maybe it's stopped.
Like the way that
So I think
I would press it.
have some sort of don't make it too complicated.
Yeah, something I definitely noticed. But it was so simple. It was easy. Like I don't know now. It's still just making sense to my brain. I got a bit better at it.
also we don't
Ideally, I would have
I think I'm getting
Well, that's what
finish one of the and then
more towards the direction.
just like actually organize my files and things.
I do
Doing it very Seems like there's
Yeah, I guess he's what
especially when also like they're really set up now and yeah, I'm sure it's a project you do end up like I said, makes you being lazy, just carrying
Yeah.
sort of stuff. So,
I would think of scrap folders and
Especially the packages. Yeah, maybe there's a way to not. That's true.
Otherwise, it's kind of like it's scared.
Yeah, I think like a
Thank you, everybody. Thank you. I hope that gives you some extra inspiration on what you might want to try. And maybe also made you a little proud of maybe there's one moment where you actually were organized. That's always nice. So going into the deep learning code base, I need to give you a quick overview of what it means to do deep learning. So in our deep learning pipeline, we usually have a big stack of data that might be 10 gigabyte, 100 gigabyte, maybe even 6.5 terabyte. This is stored somewhere on a hard drive, maybe an external hard drive or a quicker SSD drive. Now, in order to use data from this chunk of data, we want to load one sample at a time or one batch, one collection of samples at a time, and not all together. So we open this this sample, and upon opening, we might add some data augmentation, some form of flips, some form of color blurs to increase the diversity of our image. Those transformations we don't do on the stored data stack, but only upon loading the data. So in this case, we're loading a drone image of a street scene, and we want to do a segmentation, meaning that we want to have predict blue pixel values for buildings, yellow pixel values for cars. The way this works is this input image is now represented as a matrix of 3 channels by, let's say, 128 by 256 pixels. So this matrix of pixel values, they are being fed into multiple layers. That's our deep neural network, our ResNet, our YOLO, that has a lot of layers in it. For example, in this case, a convolution, the max pool, ReLU, softmax, those terms might seem unfamiliar to you, and Suzanne will go over most of them in her lecture next Monday. So essentially, those are multiplications and nonlinear functions that act on the pixel values of your input image. Once those nonlinear functions were applied to your input image, you will have some form of prediction. In this case, the prediction is not fully perfect. In your case, it might be fully perfect and you don't have to do anything anymore. But in case it's not fully perfect, you have a loss function. That loss function measures the distance in between the ground truth, meaning the prediction that you wanted to achieve and your actual prediction. In this case, the loss function might be pixel-wise distance, meaning that we look at every pixel and the corresponding pixel in the other image, and then we measure the distance of those two values. Like, for example, if the one is white, that's usually a 255, and then if the other one is blue, that might be a 49. So the distance is 190. So this loss, then multiplied and averaged over the whole image, is back propagated, meaning passed throughout your layer and throughout every layer in your model, and then through some intelligent algorithms, the parameters in each model are updated so that next time so that when you take the next image and you feed it again through the models, it'll produce a prediction that's a little bit closer to the ground truth. How exactly that backward pass is goes beyond this lecture, but will also, I think, be addressed in Suzanne's lecture. So in the code, though, all machine learning methods have basically the same setup, and we represent them in the following structure, where there is this source folder, CT classifier, that has an init.py, which registers the folder as Python module, meaning that now once you have that init.py, you can go into your Python code and write in the very top import CT classifier, or from CT classifier import dataset. Then you have the dataset. That dataset contains code on how to load the data from your memory. You have multiple models, again, registering them with an init.py. For example, you want to try out ResNet, you want to try out YOLO. And then a script to train the models. And you can see that modularity again here. Ideally, we can have multiple models, but all of the models, they use the same train.py. So in train.py, I might only want to give a little bit of a config parameter, and that config parameter specifies which model you're trying right now. And then lastly, a test.py that is executed after the model is trained to evaluate the quality of your performance, of the model's performance. So going back to the diagram, the dataset.py does the data loading, the models are those layers, and then the train.py contains all the red arrows, sort of organizing this whole structure. So diving one step further into the dataset.py, here it's important to notice that the reason why we write dataset and why we write this dataset class in the way that we write it is because it's a structure that's recommended by PyTorch. And if we do write in this specific structure that we're recommending here, then PyTorch can help us with a lot of things from their backbone, from all the software engineers that have coded over the years this deep learning library. So the structure says, let's import this parent class dataset from PyTorch and create our own class called myDataset that inherits from this dataset. Now there's the instructor that creates the dataset class. That instructor, we can give them parameters such as the path to our data folder, or also some form of list of data augmentations that we want to apply. And then most importantly, probably for this dataset class, is this self.data. The self.data is not a storage of all the data in your system, but only a list of file paths that indexes that helps the model find your sample. So this is only a list of file paths, and you should not load all data into this object, into this variable. Self.transform, there's a lecture next Thursday, I think, about which data augmentations to apply and how exactly to write the self.transform. Once the dataset is initialized, it has some helper functions such as length, which gives you directly the number of samples in your dataset. And then getItem, and getItem is this blue arrow from before that pulls exactly one sample or exactly one batch, which is one set of samples such as A1632 into memory. And the way it is pulled into memory is here you have that data list, you index it with 0, 1, 2, you get one item, one file path. That file path is opened by some library, for example, pillow image. And then that is where now actually the sample is transformed from your storage into your memory, or into your RAM, into your memory. And then you apply some transformations onto that image, you somehow extract the label, and then this getItem returns one pair of image and label that the model then can use. So the data set.py has loaded one sample, it has loaded the input image and the ground truth, and now we're feeding that through the forward pass. Model again is a class with multiple functions. Here we're again helping using the help from PyTorch, which tells us that our class, which is in this case called myResNet, has a parent called nn.module, which is sort of like the PyTorch model class. And then we initialize this ResNet, this model, we pass it some parameters such as the number of classes that we want. And then basically each model in deep learning has building blocks that look like this, where there's some form of feature extraction. And then at the end, there's some last layer or some output layer that makes the feature extraction look like the actual classification that you want of confidence values, for example. And this ResNet 18 that we're importing from PyTorch, that's also no black magic. I can actually click on that source code, and then on the PyTorch web page, I can see, oh, it does things like self.conf, batch norm, relu, conf, that again, Suzanne will explain in more detail. So the model is now defined, and that sort of defines, like, here's the weight multiplications that we can do. And now once one sample is loaded, then we actually need to apply those multiplications with the weights. So this is done by the forward function. The forward says, this is our input image. And then for this given input image, we apply the feature extractor. And then once we have all the features, we apply that output layer that forms it into some form of prediction. So now we have a prediction. And with the prediction, now we want to do the loss and the backward pass. So now we do in the train.py. And the train.py is the organizer, the manager of everything that's happening here, because it first creates the data set, it instantiates it, it creates a data loader. And now this is what I meant with PyTorch will be helpful if you write our data set in the way that we do write it, because now that we have a PyTorch data set, we can use the PyTorch data loader, which will help us do all kinds of parallel processing without us needing to worry about what actually does parallel processing mean. Do we do data and how exactly to distribute multiple samples across the GPU. That's all handled by the data loader then. We instantiate the model, and then we iterate over all the samples in our data set by loading. So this for loop that sort of calls the get item that we defined earlier. And then once we have the item, the data, and the label, we send it from the memory to the GPU by saying .CUDA. And then we have it loaded onto the GPU, and then we query our forward in the model, which gives us the prediction. So now with the prediction in hand, we want to do that backward pass. And in a very simplified way, possibly oversimplified way, training the model kind of works like gradient descent. Gradient descent meaning, let's imagine our function that we want to optimize, sort of our classifier performance, looks like this, and we want to find that minimum, that loss in the very bottom. So what we do have is we have an initial weight. This is how we initialize our model. And that in this case, we have exactly one weight. In practice, we might have a billion. So it was a bit hard to draw, so that I decided to draw it in 1D. So the initial weight, and then after initialization, we calculate the gradient. That was done by the loss function that you might implement. That loss gradient tells the model, tells the optimizer in which direction to send that weight to be closer to the ground truth. So we do that weight update. That's the length of this arrow to go towards the minimum is also proportional to the learning rate that I mentioned earlier. After multiple of those steps, of those backward passes, which are which are called iterations, we reach some form of minimum. So the same thing happens here. We define an optimizer, not gradient descent, but in this case, stochastic gradients descent, you might also have heard of RMS prop or Atom optimizer, which are popular ones. We give it some form of learning rate and other hyperparameters. And then after instantiating that optimizer, here we're actually calling that optimization. There's some form of a unique Python thing, PyTorch thing here, where we have to set where we have to set the gradients to 0 first, because they're sort of like stored and accumulate in the model. So this function, it actually calculates the loss criterion. You have defined that hopefully somewhere else. It calculates the loss. The loss is propagated backward through the model, and then the optimizer actually changes the weights of the model. And then lastly, we do the logging of what just happened. Okay, that was the deep learning code setup, and we've also done the hyperparameter experiment. Lastly, how to monitor the model training. Before I go into that, are there any questions about the train.py, dataset.py, or about the model.py? Yeah.
I'm just wondering, with the ground truth image, is that the representation of the input image that we're feeding into the model? Because sometimes people use ground truth image and input image like interchangeably. So like in your example, it was already coded in, I don't know if they were the RGB channels, or so that's presumably how the model is actually seeing your input image, rather than like the JPEG or whatever we'd be viewing on our computers. Yeah, just wondering if that's
I see. Yeah, maybe it is a question of terminology, what it means when we say ground truth image. So here the data loader spits out the data and a label pair. The data, we call that the input image, or the the input image, and then the label is also called the label, target, or ground truth.
okay.
Yep. I hope that clarifies the question.
Yes, yeah, just sometimes people use them interchangeably, I think.
Yeah, that makes sense. Yeah. Any other question? Okay. So how to monitor the model training? Reasons to monitor your model training is that it does take a long time. I think we are recommending models that train in about 6 hours or overnight, but in practice also, I think the ChatGPT was trained over 3 months or 6 months or something like that. So then we want to make sure that if we do spend so much time, money, and also climate resources, energy onto a supercomputer, a hyperparameter optimization, that we do know exactly what's going on. In our case, we want to know things like, is my model still running? Is my model trained correctly? And when can I stop the training so that I can run the next experiment? Also, I want to know how the accuracy is doing over time. And lastly, for reproducibility. What you can and might want to monitor during the training progress is the loss, the evaluation metrics such as accuracy and recall, and some application-dependent information. I often work with generative vision modeling, meaning that I want to plot the actual images that my model is predicting, or maybe I want to plot the segmentations. Maybe I want to do some sanity checks, like plotting the bounding boxes onto an image to see whether I got the coordinates right, or maybe I've accidentally flipped my images somewhere. So those are good things to monitor during the training process. Important also to monitor both the performance on the training and on the validation data set. And these are the possible curves that could look like. What is good when you have your model training on Friday kind of looks like this. What's not so good looks like this. And I cannot go into this in detail, but Shira will tell you about what exactly these curves mean, what means overfitting, underfitting. This means that you most likely have error in your loss function in the minus sign, or there's some form of garbage going on. This means that there's likely you are not optimizing the right metric, or your model or your prediction task is just way too hard for the model to do. This means that you're overfitting because the training loss is so much lower than the validation loss, and this means that you're about right. This can also mean that you're underfitting.
Except for if you're, Cheryl will talk about it more, but if you're testing on out of distribution data, often the very best thing you can expect is that version where the loss function for your out of distribution set is going to be much higher than your training loss because there's that distribution shift.
Thanks. Yeah, that's a good point. Yeah. So maybe medium good.
Medium good.
But that wouldn't be here, right? Because this is the validation set part of the process, or is this, sorry, I'm still a bit.
Oh, I mean, if your
Later on.
validation is out of distribution and your test is out of distribution.
Oh, okay, okay.
I mean, basically, this can reflect both your choice of metric, but also your choice of split.
Got it.
I think the important thing here is if you start to see that thing on the bottom left where all the loss is going up, then something's just wrong. You should kill training and you should try and figure out what went wrong.
Yeah. Another point to kill training would be if you see the loss plateauing and then it just goes on and on to be the same, then you can also kill it. Most likely it will not all of a sudden go way down again.
Can you monitor this in real time, or do you just have to? Okay.
Yes, yeah, you can monitor in real time, and the next slide tells us how to do so. So to monitor it, we need to save our models, and we need to log our models. So usually this is done every nth epoch. An epoch consists of multiple iterations. An iteration means one update of the weights, given one batch or one sample, and then an epoch means we are once over the full data set. And then in every epoch, we go once over the full data set that we have. So every nth epoch, depending on how big your data set is, you want to store the model so that in case something happens, the computer dies, somebody updated the CUDA version without you knowing about it, then you have some checkpoint stored. And that you can do with this code that I don't go into detail with, but it is in the GitHub. You have the model saved, which also means you can load it again with this code. To monitor in real time, there's a lot of libraries that help us doing so that we don't have to rely on print statements. For example, weights and biases, TensorBoard, CommentML, MLflow, Neptune. We recommend for this class to use weights and biases because it has a pretty nice interface. So in this interface, it can be a little bit overwhelming, but on the left we have each experiment name. Ideally, you can give them a bit more of a descriptive name, such as then zesty sweep. But it can create us plots like this, which are incredibly helpful. So here we have the hyperparameters such as batch size, dropout, when we want to add learning rate, and the performance of that particular combination. And then using this plot, we can find out what the highest accuracy models are. And also this plot on the right, that's the inverse of that loss curve that I showed you. In this case, it's an accuracy curve. So it starts somewhere very low and then goes up. And then we can compare here various models, various hyperparameter configurations. So it's interactive. You can use weights and biases and kind of like zoom in to that high accuracy region. And then you see this sweep. That was a very good one. And we might want to just fix those hyperparameters. Yep. So all of this code, most of this code is on GitHub, written by Benjamin Kellenberger, and you can find it here using this link. We recommend this to get you started with your code.
Just a quick point there. We absolutely recommend this to get you started if you're doing classification, because it's basically the structure of a classification code base, but also a lot of the stuff that Björn just talked about in terms of how to organize like the structure of everything and how to think about like making sure you're not overwriting stuff and that models are getting saved. That's pretty general. And then in the lecture tomorrow, we're going to dig in a little bit more on how to work with other existing code bases, things like YOLO v5 or YOLO v8 or the detect run code base, and we'll do a bit of an exploration of if you're not doing something quite simple, like starting with image classification, how do you navigate these more complex models and these more complex code bases that you probably don't want to write from scratch because they're so complex?
Yeah, and the hope is that the structures we see tomorrow in the bare bones resemble what we've seen here with dataset.py, model.py, train.py, just with a lot of bells and whistles attached to them. Okay, that is it for the lecture. Questions? We have a lot of time.
For the weights and biases, that looks like a web page, maybe? Is that something that gets served locally based on your output from your training? And if so, how do you access that on like the remote computer? Do you need to do forwarding to look at it, or?
You can do.
Yeah, weights and biases. Weights and biases by default need an internet connection on the remote computer, on the computer that is running the weights and biases, and it does all the logging and the syncing automatically in the background. And then you can go on your laptop or on your smartphone, you can just access that web page and you see all the logs.
Got it, it's cloud-based.
Yeah, it doesn't require, by default, internet access on the remote computer, but there's also workarounds if your remote computer does not have internet access. That is a bit more complicated.
I think the IP of the remote machine, we will need to verify which ports are open, and actually because there's a shared node and multiple of you would be wanting to possibly look at your own training, like you can launch like one weights and biases on like one node that you open up for like visibility externally, and then another one on another node. So that is something we might need to figure out because they have a shared machine, and so we'll have to open multiple ports so that it can be sent along different port forwarding. Or you can set up port forwarding to your local machine and do it on localhost. Anyway, both are possible, but this actually, I hadn't thought about it, and this is something we'll figure out.
That's a good point. We have to figure that out, how to do the...
How to actually make sure you're not fighting for the same external port.
And then I guess one other basic question about that is, so in order to, it sounds like you need to maybe manually make calls to the weights and biases API.
You can just go on your browser and you would go like IP address : port that you specified, and it just pops up.
I'm thinking more like to pushing data to weights and biases during the training process.
Automatic.
Oh, it's automatic.
Yeah, I think there's some, in the backup of these slides, there's a slide that has exactly the code to use weights. No, sorry, it has code to use TensorBoard. We don't have code to do weights and biases. I'm sorry.
But
there's a documentation online to do that. Yeah, it's kind of the same.
It's really low code. Like it's basically set up. You set up logging. Like you import that package. You set up logging, and then it just like in your training loop. Like if you just say log like this loss or log this thing, it just automatically handles like all of like how to log that and how to visualize it, which is great. So it's just like a nice tool where you don't need to rewrite all that stuff.
I had a question on the train.py slide.
Yeah.
Maybe I missed it, but if you're able to get a function up, so does it return something at the end? Or because I've used TensorFlow before, it all kind of boils down to like a model.fit line, which you can save as an object. So it goes into a for loop here, and say like it's finished. Does it save like a model file in another folder, and you can then access that and run that, or can you add some lines that will return this at the end here?
Yeah, so this log function we can also pass. I think in the GitHub is a bit more extensive. There's also a saving the model that calls that code that I was showing at the end of every end epoch.
Yeah, okay.
Yeah, and then that model is stored physically on your SSD, and then you can call the test.py, which then opens that model checkpoint and executes the evaluation and further metrics that you might want to think about.
Okay, I see. So that's a better way. Like before, I've done like simpler versions. I just then have it a few lines below, and I like inference in the same script. But then like the better way is you can load it in the test.py script and access the model there.
Correct.
Okay, cool.
Because then that's reusable both while you're training to monitor test performance, but also afterwards to do offline additional probing and like save off like predictions for everything. So you kind of like get more bang for your buck.
Okay, cool.
Good question. Yeah. 17.
Yeah, I'm curious about these weights files that are saved after the training of a model, the .pt files. Is there like a standard that to my understanding, it's a file that stores information, no? So is there a standard, like for example, YOLO V5 or V8 or Detectron 2, do they have to respect the same standard? Or are they like this custom for each model?
Yeah, we're talking about, let's see. Yeah, so if I may rephrase, the question is, in this checkpoint folder, it contains the model checkpoints and the actual weights of our model that is trained, or halfway trained when it was a checkpoint. And you're asking about what the format of that storage is. Usually it's files like .pt, but it's a PyTorch or TensorFlow specific way to serialize all the float values that are the weights or the parameters of the model. And because those can be like 1 billion parameters, there's quite a lot of heavy math that goes into optimizing how to store that in the most efficient way. So the actual file will not be humanly readable. It's
binary file, yeah.
Yeah.
But so like, can I write a script that evaluates a weight from a YOLO V5 of one from YOLO V8 and one from Detectron 2, and that script will follow like. I guess what I'm after is like, you have the cost of format, no, for like data, for metadata, no?
Yeah.
Is there something like this for weights? Does that make sense?
I think an ideal modularity would say that you can just load the model and then call model.forward, and that would do the prediction without you having any access to the ground source, to the original source code. But in practice, I found that whenever I use somebody else's model weights, I did need to also have access to their other source code.
Yeah, like for example, I would imagine in the weights you would have access to some values like you showed on the graphs, and you could actually kind of do a post-mortem analysis, like look at what were the best parameters out there, or extract some feature maps out of them and do some visualization out of that. I'm after that actually, like how to extract information from these weights, and I would be interested in this if we cover that at some point during our
like is the question,
and if it's possible,
is the question of like, given we have a trained model that has a bunch of weights, now we want to find out, like, can we find out some form of interpretability of those weights?
Yeah, for example.
And like whether they learned interesting features such as recognizing cat ears, a cat tail. Is that the question?
Yeah.
Yeah, so that is things that are possible. It's an active research area called explainability, interpretability. You would have to see that in the reading group. And I'm not sure if we have a lecture on that. I think we do. And I think we will explain like 10 minutes on what are the possible things you can probe in your model. Yeah.
Cool.
Yeah, we have a lecture next week we have a couple that touch on this a few different ways. There's one explicitly on like fair comparisons in models and like how to think about these ablations and like when and how to change things to figure out the contribution of the different parts of the model. And there's also a lecture on how to make things better. So like now that we have our baselines, like how do you build intuition about what to try next when it inevitably is not perfect, right?
Okay, perfect. I think there was one more question. The person can talk to me afterward. So thank you so much. I hope that helped you, that will help you in the future. Stay organized. and not have have a mediocrely messy code base. Thank you. Aaron,
Yeah,
you take over.
5-minute break.